Alright, so today we're going to talk about section 3.2, which is all on exponential functions. So hopefully by the end of this video, you kind of have an idea of what an exponential function is, how to graph them with some transformations, evaluate some different kinds, and then some general applications that you will see with exponential functions. Alright, so consider this pattern. So we have 2, 4, 8, 16, 32, 64, and we're asked to, if we're given these as our y values, we kind of want to find a function that represents them. And whenever we're given like a pattern, right, we always start with our x values as being like 1, 2, 3, 4, 5, 6, and on forth. They just are the normal integer, positive integers. And so we kind of want to figure out how these all map together, right? We want to create a function. So I'm going to call this f of x, where x is going to be that 1, 2, 3, dot, 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 right? That's what we're interested in. And we want to cook up something that represents the outputs that we're getting, which are our y values. So what can I plug in for, I could plug in 1 for x, and how do I get 2 out? Well, we could either do x plus 1, right? We could do that. But if we plug in 2 for the second one, we don't get 4 out. And if you notice, 2, 4, 8, 16, 32, 64, aren't those just powers of 2? So isn't 2 to the first power? Isn't 4 2 squared? Isn't 8 2 to the third? Isn't 16 2 to the fourth? Isn't 32 2 to the fifth, and on forth and on forth? It is. So we can write this as 2 to the x, and we can put the x in the exponent. And this would give us that nth term that we're looking for, because that nth term would be 2 to the n. That's what that means. So our nth term would be 2 to the n, right, given n here. So this is what we call a sequence, or some type of a sequence, right? We're just kind of like listing out some values. And so that's why we kind of want to just figure out patterns like this. So here's a definition of an exponential function. Let b be any real number such that b is greater than 0 and b cannot equal 1. These are the most important pieces of your exponential function definition, because I'll show you in a couple minutes why this is important. Then for any real numbers x, any values you want to plug in for x, a function of the form f of x equals b to the x is an exponential function of base b. B is the base, x is the exponent. So here are some examples of some exponential functions that we have. We have 3, here's our base, and then we have x as the exponent. We have 2.718 to the x, that's fine if we have decimals, completely fine. 1/3 to the x, that's completely fine. The square root of 5 to the x, that's fine. These are all examples of exponential functions, because as long as b is any real number, which means it can't be imaginary, that's really what that's saying, can't be imaginary, it has to be greater than 0 and can't be 1. Okay, so things that aren't exponentials are going to be our quadratics, or our cubics, or our quartics, or our, to the fifth. Anything that has like x to some finite power, meaning like a number is in the exponent, that's not an exponential. That is a polynomial of some kind. So that's why we don't call that an exponential. The base of an exponential can never be negative. And so this actually has 2 different reasons why it can't be negative. The first reason is that if you were to plug in x equaling 1/2 or 1/4 or any kind of even denominator fraction, it's not going to be a real number. But x equaling 1/3 would be a real number. And so it kind of causes this issues in the domain and the range where you're having like an alternation between real and not real numbers, and you can't really do that. It's not cool. Another issue that you would have with these is that if you were to plug in just normal values, if you restricted your domain to just be all real numbers, greater than 0 or greater than 1, I guess, that are just integers, if you were to classify this into the integers, that also causes issues, because what's going to happen is this is going to have an oscillatory behavior, meaning that from negative it's going to oscillate between a negative and a positive, and it might not ever converge to a real number later on down the road. These are kind of problems that you'll explore later on in higher level maths if you're interested in those. But in our class, we're not going to dive into that because it causes tons of issues and we're just not interested in them for right now. So don't ever worry about negative numbers in the base. And if you do see that, then something went wrong because we should never have a negative in the base. Now, this is different. You can have a negative exponential, right? So you can have negative 1/3 x. That's completely fine. You just can't have the negative on the inside with the 1/3. So as long as the negative is on the outside, it's fine. Okay, and then we can't have the base equaling 1 because that's just a constant function. No matter what you put in, you're always going to get 1 out. And same thing with 0. 0 to any power is just 1, so you're also not going to have anything. So either of these are not exponentials. They're just constants. So avoid those different cases, right? And make sure you understand why those are not allowed. Okay, so graphing exponentials is pretty similar to how we've been graphing everything else all semester. Exponential functions grow much faster. They have a parent function. Here's our parabola, and if you notice, I have sketched out this nice little list of some points that we know from x squared. Right, we plug in 1, we get 1, 2, 4, 3, 9, 4, 16, and etc. So if we have 2 to the x, though, right, it starts off a little bit slower than our other function. If you notice, 1 goes to 2. Okay, that is a little bit bigger than the last one. 2, 4, that's the same point that we have from our quadratic. 3, 8 is lower than the 9, so we can see that is kind of a little bit lower. 4, 16 is the same point, but then once we get to 5, as you can see, we kind of skyrocket. Now we're 5, 32. 5 is 25 up here, and then 6 is 64. 6 is 36 here, and then 7 jumps all the way to 128. So that's kind of where the skyrocketing happens, right? As the x values get larger, the y values grow even faster than the quadratics do. And if you thought the quadratics grow kind of fast, they do, but exponentials grow way faster. And that's a lot of terms like sometimes you'll hear it in common everyday language, right? It's growing exponentially faster, or that's, something exponentially, right? That's usually a term that we use for describing something that happens in a larger quantity or like a large value. So that's kind of where that term comes from, and that's why we call them exponential functions, because they grow super, super fast. So what about 1/2 though? And so let's kind of talk about 1/2 x, and let's graph some values, plugging in some values for x. So I'm going to start with 0. If I plug in 0, I'm going to get 1, because this is a fraction, right? I kind of want to look and see what happens with this one. Let's plug in 1. I'll get 1/2. If I plug in 2, I'm going to get 1/4, right? Because 1/2 times 1/2 equals 1/4. How about 3? I get 1/8, and I'm going to keep going. So I have 0, 1, I have 1, 1/2, 2, 1/4, 3, 1/8. They're getting super small. And what happens, though, if I plug in negatives, right? What if I plugged in -1? Let's test that. If I do 1/2 to the -1 power, remember when we have negative powers, we swap. Remember, if you remember how to deal with negatives, right? You do a little flip on the inside of your fraction, so it would just be 2 to the first, which is just 2. So that gives me 2. So -1, 2. Notice that my negatives are going to make this bigger. So it almost has kind of like a reflection about it. Okay, how about graphing 5 to the x power? Let's do this one. So let's make our table of values. So let's start with 0. I plug in 0, I'm going to get 1. Let's plug in 1, I get 5. 2, 25. 3, 125. And I could keep going, but they're just going to get bigger from there. So 0, 1, 1, 5, 2, 25. It's going to grow really, really fast like this. Okay, so exponentials have horizontal asymptotes, believe it or not, at y equaling 0. So, you might have noticed that all of these graphs here, right, they all kind of don't pass through y equaling 0. And we'll learn about why this is exactly the case later on in the next section. But for right now, we just need to know that exponentials can't ever be 0, right? And think about it, right? If I had the 2 to the x and I set that equal to 0, what do I plug into my exponent to get it equal to 0? And we can't, we don't know, and there is no value we can put there that will give it 0. So that's why we have this horizontal asymptote at y equals 0. And so as long as there's no transformations going on, right, then we'll have that asymptote. So the general form of our exponential is listed here, right? B to the x, where b is greater than 0 and b cannot equal 1. And if b is greater than 1, it's going to be increasing, which we saw, right? If we go up here, 5 to the x is increasing as x values get larger, which we call an exponential growth. If it is a fraction that is the base, if the base is a fraction, then it's going to be an exponential decay, which makes sense because 1/2 was decreasing. The domain is always going to be all real numbers. You can always put in real numbers, and the range is going to be 0, not included, to infinity. And the reason being is that that's where that asymptote is. Now, again, this is as long as there is no transformations. When there's transformations, we have to be careful. The line y equals 0 is a horizontal asymptote, and the function is going to pass through 0, 1, because anything raised to the 0 power is always 1. Now, let's talk about some transformations that can occur. We have a times b to the x minus h plus k. So all of those different letters are going to have some type of transformation power over the function. If a is less than 0, meaning a is that outside constant, it is not the base. Do not think of it as the base. It's not the base. If a is less than 0, it's going to reflect across the y-axis. So it's going to flip down, which we learned all these transformations earlier on in the semester. They also apply to our exponential functions. If we have a between 0 and 1, it is going to be, it's going to shrink. Okay, so if that value on the outside is less than or in between 0 and 1, right, it's going to shrink. And if it's greater than 1, it's going to stretch if it is the absolute value of it. So again, the negative will have to do with the reflection, and then the magnitude or the amount of that a, right, how, depending on how big the number is or far away from the origin, is going to determine if it shrinks or stretches. If h is the variable in the exponent, and if h is greater than 0, you're going to shift it to the right. If it is less than 0, it is going to be shifted to the left. So if you're adding, if it's plus 3, you're shifting it to the left. If it's minus 3, you're shifting it to the right. That is how those values, that's how that's going to work. Okay, if k is going to be that added constant, so you're just adding it up and down on the axis, so it's just shifting up or down depending on the constant, depending on the value. It's very similar to everything else that we've done. And then y equals k is going to be that new asymptote depending on where it shifts. So let's graph one together. So we have 2 to the x plus 2 minus 1. So we're interested in graphing this function, and we can use some transformations to make sure that we're on the right track. And we probably don't need to plot like too many points, just because we should have an idea once we're finished graphing this one. Okay, so let's identify our asymptote first, which, remember what I said to you, the asymptote is going to be this new value. So we're going to have at y equals -1, our asymptote. Okay, 2 to the x plus 1. So I'm going to make a little mini table of values just so I get an idea. So how about we plug in 0? So we'll get 2 to the 2 minus 1, which is going to give me 3. So 0, 3 is going to be 1 point that we're going to have. And let's do maybe 1. Let's do -1. So I'm going to have 2 to the -1 plus 2 minus 1, which gives me 2 to the 1 minus 1, which gives me 1. So I have negative 1, 1. I'll say that's here. And then let's just do one more. Let's say, let's do negative 2. If I do negative 2, so I have 2 to the negative 2 plus 2 minus 1. This becomes 2 to the 0, which is 1 minus 1, which equals 0. So negative 2 is going to be 0. Okay, so I can comfortably say that I'm going to sketch it, and it should look something like this. So it's always going to be some type of an arc-like function. It kind of looks like half a parabola, but it grows a lot faster, and the curvature is a little different. Okay, so this is the main idea behind our behind graphing exponentials using the asymptotes and all that. Okay, the next thing that we need to talk about is a new number that I'm going to introduce to you. So you've probably seen this in the past, but maybe you haven't. When we have exponentials, we want to talk about something that's really, really, really important and very popular actually in math. So Euler's number is something we're going to discuss, and we're going to be very comfortable with. We need to in this class. So consider this exponential function that we have here, 1 plus 1 over x, all of that raised to the x power. So I want to kind of make a table of values for this and just see kind of what's going on. And kind of see if anything happens when I start to plug in infinitely large numbers for these different values. So let's calculate. So we have 1 plus 1 over 10. So let's plug in 10 for x and see what we get. So if we plug in 10 for x here into this function here, so we'll get 1 plus 1 over 10 to the 10th power based on the formula, which gives me 2.593742, and it keeps repeating. Let's plug in 100, so that's 1 plus 1 over 100 to the 100 power, and that's going to give me, let's add some zeros here, that's going to give me 2.704813 and some more decimals. Let's plug in 1,000, 1 over 1,000 to the 1,000th place. And I'm going to get 2.716923 and some more. So it looks like it's going to be 2.7, and let's keep going. So let's plug in 1.1 over 10,000 to the 10,000 place, and that's going to give me 2.718145. Keep going. 1 plus 1 over 100,000 to the 100,000 equals 2.718268 and some more decimals. And let's do 1 million just for fun. 1, 2, 3, all over to the 1, 2, 3, 1, 2. And you get 2.718280 and some decimals. And so essentially what we're interested in is when x becomes infinity, if I plug in 1 over infinity to the infinity. This is some illegal math stuff. Dividing by infinity is not usually allowed. And then that infinity on the outside requires you to do some math skills that we haven't quite mastered yet, to actually evaluate what would happen if you plugged in infinity into this function. And so as we plug in x as infinity, we actually get it to converge to 2.718281828 and it keeps repeating, but it doesn't repeat it doesn't repeat the numbers and the digits in the same order. So it's just randomized. It's super random, and we call this number E. We call this Euler's number E. It's the exponential number. It's just E. And so what this does is it actually is very useful in a lot of different things. And so you're just going to need to memorize kind of that E equals is approximate. We use these little squigglies when we want to say approximate 2.718. It's usually the round that we use. E is a transcendental number. And so transcendental numbers have non-repeating and non-terminating decimals. And another one that you might be familiar with is pi, right? Pi is approximately 3.14159, and it also has more repeating digits, which we also use commonly. So also plugging an I into E's will also give you a transcendental number. So it's just another kind of number. And so here's a nice diagram that I like. I've used this before in some of my academic papers I've written. And I just think it's a really nice diagram that shows kind of the different kinds of numbers that exist. And so the complex plane extends to all numbers, because you can always write it as, remember, complex numbers is A plus BI. And so if B is 0, then we're going to have the real numbers. When B is 0, that's when we get the real numbers. And so you kind of have this like overlap in the transcendentals. You have irrational numbers, right? And so you kind of just, there's a lot of different things. Here's all of our numbers that we use: the reals, the algebraics, the rationals, integers, whole numbers, natural numbers. There's just kind of, this is just what we use in math, right, to denote all of our number systems. And so it's a helpful chart to have if you ever see any of this notation. It just is pretty helpful. Okay, so EDX graphs, just like all the other exponentials, it looks identical to it looks very similar to the 2 to the x, which is what we graphed earlier, but again, it has that added decimals, so it doesn't matter, right? It's gonna look a little bit different, but other than that, it really doesn't look too different. So that's E. E is going to be very helpful. And we'll talk about its inverse later on in this chapter. And if you watch section 3.1, you should know all about inverses. All right, so the last thing that I want to talk about is applications. And so now that we've acquired this helpful E number, Euler's number, we can actually talk about some really cool investment type of problems. And so something that's really, really important is compounding interest. And compounding interest uses this idea of, as n goes to infinity, what is the values? So we have 3 different formulas that you're going to see and you're going to use in this class that have to do with interest. And so this first formula, I equals PRT, is interest equals principal times the rate times the time. So principal is going to be however much money you're putting down into the bank or into some type of a loan or whatever you're doing. Or rate is going to be the percentage that it's earning or that you're paying or whatever you're going to be doing. And then T is going to be the amount of time. A equals P times 1 plus R over N to the NT is going to be another help formula, but this tells you the future value after T years, compounding, and periods. So this is when you start to get into more complex things, and so you want to be very careful. And then A equals PE to the RT is continuous compounding, right? Simple interest is great, but a lot of times we don't have a simple interest, right? And bank accounts don't do that. Mortgage calculations also are a little bit different. And if you're interested in that, feel free to reach out. And you could also just do a quick Google search and find my thesis, which was on mortgage calculations. And so they use a little bit of a different formula that has more variables and such in them because they're using different kinds of calculations. So all of this idea, though, all of these have this kind of E in them, right? This exponential. And if you look in this, the second one here, it even has this 1 plus R over N, which looks very similar to our formula for E up here, right? 1 plus 1 over X to the X. It's very similar. It's very, very similar. So that should be striking to us. This should be kind of reminding us what that is. Okay, so suppose that we have $5,000 invested and it earns 6.5% per year. So that's the percentage of interest that we are earning. And we're putting $5,000 into this account. So this would be probably like maybe some type of like a bank account that's earning interest. Stocks and bonds have their own thing going on. They have their own formulas. So they're not necessarily going to be just like this. So you have to be careful, though, of exactly the kind of problem that we're trying to do. So we just want to be careful of that. Okay, so if we're compounding for 1 year, we want to calculate the interest that we are earning. And so the first one doesn't necessarily... So we're going to want to be careful with the formula that we choose. And we're going to use, since this is annually, we're going to use the A equals... We're going to use A equals P times 1 plus R over N to the NT. That's the formula we're going to generally use. So if annually, N is going to be the amount of time, which is going to be 1, or how many compounding intervals there are. Since we're compounding yearly, it's going to be 1 year. Okay, so since N is going to be the intervals, so it's not necessarily dependent on time. It's dependent on how many times it's accumulated. So since it's compounded yearly, N equals 1. 1 year, it's compounded once, right? So now we just plug it in. So we get P is the principal, so that's 5,000 times 1 plus the rate, which is 0.065. Remember, we got to move our decimal. Our N is going to be 1. And we need the time. So we are going to invest 10 years. So we are doing this for 10 years. So we have 1 times 10. And if I plug this in, I will get 9,385.69 for 10 years. So that's kind of a good result on our investment, or a good return for investment. It's a high percentage, right? So you're not really going to earn that in the real world. You probably earn maybe like a couple percent. Just 6 is a lot more. Okay, so compounded quarterly, we're interested. N is going to be 4. That's how many intervals we have quarterly. So we have 5,000. We're using the same formula from above, plus 0.065 all over 4 times 4 times 10 to the 4 times 10. So we get 9,527.79. Monthly, N is going to be 12, since there's 12 months, right, that we're going to be doing. And so now we have 5,000 times 1 plus 0.065 all over 12 times 4, 12 times 10. So we get 9,560.92. We have daily, that's N equals 365 in that interval, right? How many times is it doing it in that year for the 10 years? It's 365 times, right? Compounded daily. Technically, that's actually what mortgages compound if you read into them, but they have their own different calculation. So 1 plus 0.065 over 365 to the 365 times 10, and we'll get 9,577.15. And how about if we do it continuously? We need to use A equals PERT. We can't use the other one because we're plugging in N equaling infinity. So we will get P, which is 5,000, E to the 0.065, which is our rate, times 10 years, which gives me 9,577.70. So that's going to be how we calculate using these formulas. So it's really just plug and chug, right? Just plug in the numbers and calculate it. Remember that the formula that we were originally using does converge to A equals PE to the RT as N approaches infinity and gets back. Okay, so other applications that you're going to see in with exponentials is bacteria growth, population modeling, which is what your project is going to be on. Project 3 is going to be on COVID spread and modeling, using the NIH's paper on a study that they did in Peru for vaccination versus cases. radioactive decay, carbon dating and fossils, temperature and cooling, financial interest calculations. So one thing I did want to just bring to your attention is Newton's law of cooling, which is a really, really cool thing that they have. So one of the most popular word problems that you'll encounter is if you're leaving a cup of coffee out on the counter, how long until it reaches equilibrium or reaches room temperature? And that's probably something that you might encounter. And so we have this formula T of T, which is temperature of time, equals T sub S plus T sub 0 minus T sub S times e to the negative kt. So T is going to be time that is elapsing. T of S is going to be the temperature of the environment at which your cup is sitting out or whatever you're in. So, right, if you're in a house, it's going to be temperature controlled, or if you're outside, it's temperature, right? There's a specific temperature or room temperature, whatever your problem is asking. T sub 0 is going to be your start temperature of the object. How hot is it or how cold is it initially? E is going to be that Euler's number, our E constant. And then K is some constant that's going to depend on the surface area and the materials, which will vary. And a lot of times different depending on the problem. They're either going to give you a finite number or they're going to have an entire equation dedicated just to the K, or they're going to vary it or of some sort. And so that's kind of where you do have to be careful. But this is a really cool formula that is pretty popular in this kind of stuff, and it uses that E. And so if you do look at the exponent, right, it is negative, which does kind of imply, right, the negative exponent, it, as the values get bigger for time, and granted that K is going to be positive, it should kind of decrease, which should make sense, because if you're starting off with a hot coffee and you're letting it sit out, it will cool over time. So that's the whole idea behind exponential functions and what we're interested in learning from them. And so overall, this is not anything different from what we've been studying this semester with different kinds of functions. We just are introducing a new function. All right, so that's going to be section 3.2.